Hello everyone, I am Chuan Xu. I'm glad to be here to present our work. What else is needed when eavesdropping federated learning? In CCS workshop Privacy Preserving Machine Learning. This is a joint work with Giovanni Neglia. To start, I'd like to briefly go through what is federated learning. Original federated learning enables a large amount of clients such as mobiles or IoT devices, cooperate together to train a global model without transferring data. We can see from the formula that the global model, theta star, minimizes the weighted sum of the client's empirical loss. As the data is always kept locally, can federated learning really protect clients' privacy, even against a weak adversary who is just eavesdropping the channels? This adversary is called honest but just curious. Recently, multiple work has shown that by inverting the gradient transfer between the server and the client, it is possible for the adversary to reconstruct the image to a recognizable level. Besides, with some assumptions on the adversary's pre-knowledge, the adversary can infer whether a given data instance is used in the training and when a property appears or disappears in the local data during the training. In our work, we introduce another possible attack that may further motivate the privacy-preserving methods for machine learning as concerned by this workshop. Our attack is called local model reconstruction attack. The goal is simple. The adversary aims to reconstruct the model a client will have trained using only its own local dataset. Having this local model is dangerous, as the local model usually overfits more the client's data than the global model, and it reviews the client's behavior. Therefore, it enhances the performance of other attacks introduced for centralized setting, such as the attribute inference and the model inversion attacks. Moreover, it enables the membership inference attack without prior knowledge on the client's dataset. So to show the interest of our reconstruction attack, I give a small example here. Suppose that we have two clients. The data sample of the clients contains two values, x and y. X can be seen as the feature, and y is the observation. We use the linear model, which predicts y giving x. Under such data distribution, the federated learning process may learn the global model, presented by the orange line here, while the local models of the client 1 and the client 2 are the gray line and the green line. Now, suppose X is the public information that the adversary has access to, and Y is the private information that the client would not be willing to let the others to know. If the adversary could reconstruct the local model, it can then access to this private information. So before we go into the detail on how to perform such a local reconstruction attack, first, I'd like to emphasize more on the adversary we consider. As mentioned, the adversary is honest but curious. It does not interfere with the training process, and it knows the structure of the training model, loss function, as well as the training algorithm. These are the common assumptions made for the attacks we mentioned before. Second, the attack targets a federated learning framework which consists of the following three steps. At each iteration, the server selects the clients and broadcasts the global model. The chosen clients update their local model and return them to the server. Then the server aggregates the received client's model. Note that we consider the framework that there's no secure aggregation protocol. Secure aggregation protocols would prevent our attack as the identity information is lost after secure aggregation. But they do require significant additional computation. A majority of the federated learning algorithms fit into this framework, including the first proposed one, fed averaging. The server uniformly selects a subset of the of the clients, and the chosen clients run a stochastic gradient descent for multiple local A box. In the end, the server does weighted average over all the received models. So in one word, our work started how to perform local model reconstruction by eavesdropping such a federated learning framework. The first, we showed a possible case to reconstruct the exact local model when training through federated learning averaging. Moreover, we showed that at least one client's local model can be reconstructed, and our attack solution is optimal in terms of the numbers of runs eavesdropped. Second, we propose a heuristic for attacking on general machine learning problems and algorithms for federated learning. The special case we consider is a linear least square regression through federated learning average algorithm with food batch size. Suppose that the data has D features. First, our observation shows that once the client has communicated with the server for the order of D times, the adversary can recover the exact client's local optimal model in the order of D cube operations. The attack method behind is based on the observation that federated averaging with food batch size, the difference between the broadcasted global model and the returned local model is linear to the broadcasted global model. Once we succeed to find out the mapping coefficient W and V, we can rebuild the exact local model. Notice that our attack solution does not require any knowledge on the learning rate and number of local A box in federated averaging algorithm. Then you may come to a question that, is it possible that no client needs to communicate with the server for more than D times to finish the training? Of course, if at the beginning of the training, the initial model is already optimal, no client needs to communicate. But we will build an extreme case here, where at least one client needs to communicate with the server for the order of D times, if we want to ensure the global model is optimal. In another way of saying, applying our previous attack solution, at least one client's local model can be reconstructed. Here, we build a scenario of two clients, where the global optimal model contains only non-zero values, and the local model for client 2 contains only zeros. Here, the dimension of the features is 4. The initial global model is of zeros. To show that we need at least 4 iterations, I will build the client's once loss function in the sense that the return local model here turns only 1 0 to non-zero from the received global model. And the client's 2's loss function is built in the sense that the returned local model has the same pattern as the received global model for zeros and non-zeros. Here are the corresponding local loss function. So we can see that in order to make sure the final global model is of non-zeros, client 1 needs to communicate with the server for at least order of D times. Then you may wonder if there exists any better attack for the adversary that it does not need to wait for the order of D communications. The answer is no, which means that our attack is optimal in terms of the numbers of runs eavesdropped. To prove it, we built 2 scenarios, here and here, where the client 1 has different local loss function. In these 2 scenarios, and the first D-1 communication runs, the adversary would have the exact same observations. So the adversary must wait for the div communication run to tell the local model of the client 1. Till now, we have just considered a really special case for the attack. The starting problem is just linear least square regression, and algorithm is a federated learning averaging with full batch size. Now, we propose a heuristic for the local model reconstruction for any machine learning problem and any algorithm falling into the federated learning framework. The heuristic consists of 3 steps. First, the adversary keeps connecting the exchange message during the training, and it builds its own dataset where the data sample contains 2 vectors. The first one is the broadcast model, theta, from the server to the target client. And the second one is the difference between the broadcast model and the returned model. This difference is denoted by the delta theta. After the connection, the adversary builds a mapping function, GC here, to predict the delta theta, giving the theta. Then the adversary estimates the local model by minimizing the long square of the mapping function. Because if the input delta is the local model, is the local optimal model, the delta theta should be close to 0. The performance for this heuristic depends on 2 aspects. First, how well the mapping function mimics the local update rule applying on the client. More randomness is involved in the local update rule, harder for the adversary to find the mapping function. Second, how close the estimated solution is to the true minimizer of the final optimization problem. And this will depend on the convexity of the mapping function. We have conducted 2 experiments to test our heuristic on logistic regression tasks. The first one is on the leaf synthetic dataset, where there are 5 clients with different number of samples. We evaluate the average train local accuracy over 10 independent runs. For the decoded model, higher the training accuracy, better the performance of our attack. We compare our decoded model for each of these 5 clients with the baseline, which is the last returned local model by each client. The last returned local model is more susceptible to attacks than the final global model, as it contains more personal information. And we can see from this table, the last column, that the average that our attack on average outperforms the baseline with 10 to 20% improvement. And it is quite insensitive to the number of the local steps. The second dataset we consider is the LDOT one, which is used to predict whether a person has an income larger than $50,000 per year. We split data among 10 clients in the way that the first 3 clients only have information on the PhDs of different ranges of age, and the other clients have the rest of the data uniformly distributed. On the left, we show the performance of the mapping function when attacking one of the first 3 clients on the different batch size scenario. Small batch size will introduce more randomness into the dataset. Thus, the mapping loss is higher for small batch size. On the right, we show that the decoded local model outperforms the baseline, which is the dashed line, for the test accuracy as well. So to conclude, in this work, we initialize the starting of a new attack for federated learning. Our attack does not suffer from the learning with large batch size, and is quite insensitive to the local steps. For the future work, we like to improve the proposed heuristic to reconstruct more complex models and make connection between the attack and the privacy-preserving algorithm. And thank you very much for your attention.